So our next presenter, Spencer Padgett, Buffelgrass growth within urban subhabitats using high-resolution aerial photography.
All right, thank you, Chris. My name is Spencer Padgett, and I'm here tonight to talk to you about buffelgrass growth within urban subhabitats using high-resolution aerial photography. I want to start by giving a brief introduction of what this project will go over. Tonight we will cover what is buffelgrass and why it is an invasive species within the Sonoran Desert habitat, why we need to map and monitor buffelgrass, and the shortcomings of previous techniques used, an overview of the data, an introduction to the study area and the subhabitats that were chosen for the analysis, how supervised classifications were used to locate buffelgrass within each scene, how conditional statements were used to isolate the buffelgrass land cover from these classified images, and then using these isolated or binary classifications to perform image differencing on sequential year sets to locate areas of growth, loss, and no change. Then we're going to identify large colonies of buffelgrass with these binary reclassifications to calculate patch size over the years. And finally, some results and conclusions for the analysis. The first question that may need answering is, what exactly is buffelgrass? Buffelgrass is a bunch grass that is native to most of Africa and can be found in southern Asia and arid Europe. It can start as a short shrubby grass and can grow to be a few feet in height and diameter. Older plants branch profusely and produce new leaves and flower spikes very quickly after light rains, making buffelgrass an extremely prolific seed producer. These seeds can be spread a number of ways, including wind, runoff, wildlife, people, and vehicles, and other disturbance. It has fire-prone characteristics that make it a nightmare for wildfire control. Buffelgrass was introduced in the 1940s by the U.S. Soil and Conservation Service for livestock forage and erosion control. It was in planting trials at the Soil Conservation Service nursery in Tucson from 1938 to 1952. In Oregon Pipe Cactus National Monument, buffelgrass was rare before 1984, but by 1994 it had occupied nearly 20 to 25 square miles and was expanding rapidly. Few people other than botanists noticed buffelgrass in Arizona before 1990, but today it is difficult not to see it in the southern half of the state. Buffelgrass is a huge problem in southern Arizona for two primary reasons. One is that buffelgrass will invade the space between native Sonoran Desert vegetation normally occupied by soil and rocks and create wildfire linkages that can expose this native vegetation to wildfire. Buffelgrass also has the ability to regrow after wildfire, whereas native desert vegetation will typically just die. Secondly, buffelgrass grows densely and can crowd out native vegetation of similar size, and it can also outcompete larger native vegetation for nutrients and water, and its dense root network and ground shading can prevent the germination of native seeds. Now, why map buffelgrass? Simply put, buffelgrass is an invasive species that requires monitoring. The Sonoran Desert is a rich biological ecosystem which is visited by millions of tourists every year. Without proper monitoring and mapping of this species, buffelgrass will continue to grow and destroy parts of the Sonoran Desert and could cause a decrease in tourism over the many decades to follow. Invasion of buffelgrass into the urban core and national park systems creates high wildfire risk, which could have devastating safety risks to the general public. Previous mapping techniques of buffelgrass include ground surveying and aerial mapping. Ground surveying by foot takes extensive time and money and can be dangerous due to the desert's extreme heat and harsh environmental conditions. Mapping by air is also extremely expensive as it requires the contracting of private flights, either small aircraft or helicopters, and is only accurate to what the mapper can pick up with his or her trained eye as they are flown over an infested area. Part of this project was to assess the feasibility of using free high spatial resolution orthophotography, remote sensing, and GIS software to map and monitor buffelgrass within a scene. For my study area, I wanted to choose a location that mimicked both the undisturbed Sonoran Desert and urban land cover encroachment into the Sonoran Desert. I chose the Tucson Airport Authority as the location for this project for a few reasons. First, the TAA is a huge 8,080-acre parcel located south of downtown, nestled between the I-10 and I-19 freeways. There's free high-resolution orthophotography available for this area. The area is included in a Southern Arizona Buffelgrass Coordination Center research grant, which included surveyed buffelgrass locations within the TAA boundary, which would become important data for identifying buffelgrass correctly in the orthophotos. And finally, the TAA contained vast areas of undisturbed desert as well as urban aviation infrastructure that could be broken down into urban subhabitats as well as other subhabitats that could influence different growth patterns of buffelgrass. To begin my analysis of buffelgrass in the TAA, I first needed to collect some data. The two main pieces of data I needed were the buffelgrass patch locations and high spatial resolution orthophotos of the TAA. Since the buffelgrass patch vector data was provided by the SABCC, I mainly needed to focus on acquiring high resolution orthophotos. With buffelgrass, or any ground vegetation for that matter, it is important to understand the scale at which you are mapping. Buffelgrass shows up incredibly small on most aerial photography, so you need to have good spatial resolution to correctly interpret it from other desert land cover types, especially at the plant scale. Unfortunately, most satellite imagery is too expensive to get at this fine of a resolution, and free satellite imagery products such as Landsat and MODIS are either 30 meter or greater spatial resolution, which is inadequate for mapping buffelgrass because each pixel is too generalized of the land cover types it represents. I was lucky enough to acquire orthophotos from the Pima Association of Governments, which had all the correct imagery I needed. I collected data from 2000, 2005, 2008, and 2011. All those dates had different, all of them had different flight dates, so the buffelgrass showed up slightly different in each scene, from brown all the way to green. And all this was in 1 foot resolution with the exception of 2011. All that data was resampled to have the same resolution as the 3 other dates prior. 2011 also contained a 4th band, near-infrared band, which is useful for identifying vegetation, but since the other 3 dates did not include them, it was omitted from the analysis. This map shows the buffelgrass locations within the TAA property which was represented as the buffelgrass vector data layer provided by the SABCC. I wanted to choose areas that were a mix of both urban and desert, as well as places with high and low disturbance. As you can see in this map, most of the buffelgrass grows near the northwest corner of the property, near all the urban land cover types. There is a highly disturbed gravel pit located to the south of the airport that was also subject to one of the subhabitats, or was also included as one of the subhabitats. So between the combination of density and location, I chose these 4 study groups. Study group 1 is the main terminal tarmac area of the airport. Group 2 is the highly disturbed gravel pit south of the airport. Group 3 is some more urban infrastructure land cover types and a wash going through there to represent a more riparian subhabitat. And group 4 is the most undisturbed of the 4 groups, being to the southeast of the main airport, mostly undisturbed Sonoran Desert. So after breaking up the TAA into 4 different subhabitats, within each of those subhabitats, I performed a supervised classification, accuracy assessments to evaluate these classifications, binary reclassifications to isolate the buffelgrass, and then image differencing between these binary reclassifications to show areas of growth, loss, and no change. And then where it was applicable, mostly in the urban subhabitats, you could digitize larger buffelgrass colony locations and calculate their geometry. So the most important part of this analysis was to correctly identify buffelgrass from any other land cover type, more importantly, desert vegetation. Identification was done through ERDAS Imagine supervised classification tool. With this tool, a user selects a group of pixels to define a particular land cover class. The user can then go back and choose additional pixels to be combined into the same class to get a good variation of each land cover type within a scene. Buffelgrass vector data was overlaid to all the orthophotos to correctly identify buffelgrass within each scene to study its tone, complexion, and patterning. Each land cover class is then stored in the supervised classification signature editor, where pixel reflectance values are recorded for the classification algorithm. After all land cover classes are defined by the user, the computer then takes every pixel in the scene and categorizes it based on these land cover classes that the user has defined. In the image to the left, we see a group of pixels being selected. This is actually Buffelgrass in between, in a field between the tarmac at the main airport. And then these values are then loaded into the signature editor, which is the chart beneath that image. And it shows all the different land cover types for this particular scene, the reflectance values in the red, green, and blue bands, the pixel count for each of these scenes, and a raster value for each of these land cover types that will be useful for the con statements coming up. So this is the image of when you run a supervised classification. This is 2008, group 1. So every pixel now is represented by one of these 9 land cover types. And then with this, the next step in the analysis was to isolate the Buffelgrass land cover type from all the other land cover classes to perform image differencing. To automate this process, I made a model in ArcGIS 10.1 Model Builder. A con statement was first used on each image to define every pixel representing Buffelgrass, Buffelgrass class originally given a value of 14, which would then be converted to a value of 1, while every other land cover type would be given a value of 0, creating a binary reclassification. Each binary reclassification would then be subtracted from each other to visualize areas of growth, loss, and no change through sequential year sets. And the con statement beneath the model is just the typical syntax for that. You evaluate a statement with a true or false outcome. So for the Buffelgrass, anything with 14 was given 1, everything else was given a 0. This is the product of the binary reclassification. You can really see where the Buffelgrass is growing without any distraction from any other land cover types or pixels around it. This is great for identifying areas of high density and high growth. And then from this, image differencing, this is 2002 minus 2011. And these will show areas of loss, growth, and no change. Because when you take the binary reclassifications, you either get -1, 0, or 1 as the outputs. So that correlates to loss, no change, and growth, respectively. So then within these binary reclassifications, you can then use them to digitize boundaries of larger colony locations. So with this one, group 1, 2002, I took it and I digitized the boundaries of that, overlaid it on top of some Esri base layer, and then took group 1, 2011 binary reclassification, did the same thing, digitized the boundaries of the large locations, of large colony locations, and then overlaid the two. The geometry was calculated to show a 190% increase from 2002 to 2011. This is the output of the image differencing from group 2. This is the highly disturbed gravel pit south of the airport. The lower half of the image is actually the highly disturbed gravel pit, and the upper half of the image is mostly undisturbed Sonoran Desert. You can make out growth alongside what would be piles of gravel in the disturbed gravel pit and alongside the access roads for the construction vehicles. There's a little bit more variation going on in the upper half of the screen from differences in color and complexion of soil that was classified. This is the image differencing from group 3, 2002, 2011. There's a wash going through about the diagonal of the image towards the lower left hand that shows significant growth, and there's also a bunch of Buffelgrass patches in the upper left corner of the screen that were digitized. This image really shows the boundaries of these Buffelgrass colony locations. These were also then digitized. 2002, same thing with 2011. And then overlaid, geometry is calculated to show a 155% increase in this urban subhabitat subdivision. And then finally, group 4, similar to group 2, very hard to visualize the larger Buffelgrass colonies in this one. There's a little bit of mixed pixeling going on from different different soil color and complexion in the classification images. Yes, and then finally, This graph shows the percent change of growth for all the groups and all the different year sets that were differenced. Here we can see a decrease in growth from 2002 to 2005 and 2005 to 2008 for groups 1, 2, and 3, and an increase in growth from these date sets for group 4. From 2002 to 2011, groups 2, 3, 4 showed an increase in growth of about 13.5%. Group 1 showed 7.5% growth during these dates as well. This graph shows the percent change of loss for all groups and all date sets. For groups 1 and 3, there was a loss of about 2.5% from 2002 to 2011, and groups 2 and 4 showed about a 10.5% loss. Finally, there was a strong connection between Buffelgrass growth and colony location when looking alongside roadways, tarmac, and urbanized boundaries. There was an average growth rate of 19% per year in the digitized subsections of groups 1 and 3. Locating and monitoring Buffelgrass colony locations was much more difficult in a desert scrub scene, and this project successfully integrated tools and techniques commonly found in remote sensing and GIS to produce an analysis for Buffelgrass identification and growth habits within an urban setting. And then here are all the references I've used, and finally, any questions? Anybody? Yes, Brad.
Yeah, in the medians, I noticed there were these strips.
Yeah, that just took they would take like the paint off the runway or the tarmac that needed to be classified into one of those land cover types, and Buffelgrass happened to be the one class that it closely matched the most. Yep.
Do you notice any, when you're looking at the data, did you notice any correlation between the Superfund sites that are located out there and whether there was increased or decreased growth in the Buffelgrass?
I did not take those locations into account. After I picked up these study areas, I just kind of stuck with them. But I'm sure there would be definitely some monitorable growth between, especially if there's vehicles or people going through it. Like any sort of activity in the area just shows massive growth over the years. All right, thank you.